Hello and welcome to chapter 6, which talks about thermochemistry. Uh, this chapter talks about different types of energy and especially heat as the main source of energy we have here. Before everything else, let's talk about what you have learned before, what you know from physics or maybe chemistry courses before. There are two different types of energy, or let's say there are so many types of energy, but the two main categories of energy are kinetic energy, which is energy in motion, and potential energy. So the energy in motion, which is kinetic energy, is calculated from this formula. Kinetic energy is half of mass times velocity squared. Mass is expressed in kilograms. Velocity or rate or speed is expressed in meters per second. So the total of these units altogether will be joule, which is kilogram meter squared per second squared. Kilogram from mass and meter squared divided by second squared from velocity squared. Another unit for energy is calorie, and here is the conversion between calorie and joule. Each calorie is 4.184 joules. Another type of energy we talked about is potential energy. Potential energy is because of the position of an object. So if I hold this marker or pen here, the position of this marker is going to give it potential energy. So how you calculate potential energy? By this formula: mass times gravitational constant times height. Mass in kilogram again, gravitational constant in meter per second square. On the earth, this constant is 9.80 meters per second square. On each planet is different, and in the space is 0. So height is in meter. So again, unit for potential energy will be joule or kilogram meter square per second square. So these are two different types of energy, and also the total of kinetic plus potential energy inside the substance is called internal energy. So internal energy, we show it in U. It will be the summation of potential energy and kinetic energy. All right. In thermodynamics, we have 3 laws. You learn one of them, or let's say first of them, in General 1, and the rest of them in General 2. First law of thermodynamics, is what you already know. You know it under law of conservation of energy. So the law of conservation of energy is the same first law of thermodynamics. What does this law say? It says that the total quantity of energy in the universe is constant. It remains constant, but it only changes from one form to another form. So that's law of conservation of energy. Energy neither created nor destroyed, but it changes from one form to another form. Now it's time to start our thermochemistry chapter by knowing those concepts about energy. Thermochemistry, thermo means heat. So thermochemistry is the study of heat which is absorbed or released by a chemical reaction. So you do a chemical reaction, it either absorbs energy or releases energy. So thermochemistry is studying these heat exchanges, and this is what we do in this chapter. Ready? So, in thermochemistry, we have 2 different parts: thermodynamic or thermochemical systems and thermodynamic surroundings. So basically, we just say system and surroundings. System is whatever you study. It can be as small as a match or very big. Thermodynamic surroundings is everything else around your system, is whatever surrounds your system. That's what we call the surroundings. So heat exchange between system and surroundings is studied in thermodynamics. So we say heat, what is heat? Heat, first of all, is shown in Q, and it's the energy, it's a type of energy that flows into or out of the system because of the difference between temperature in system and surroundings. And don't forget that heat always flows from higher to lower temperature. So heat is the amount of energy that flows from higher temperature to lower temperature between system and surroundings. I told you thermodynamics is the heat exchange between these two things, between system and surroundings. So if system absorbs heat from surroundings, the direction of heat is from surroundings into the system, you call it endothermic process. Endo means inside. So system absorbs the heat inside itself. And by convention, we consider the sign for Q positive. So whenever you see a positive sign for Q, means we're dealing with an endothermic system. Endothermic process means the system absorbs heat. But whenever a system releases heat to the surroundings, it's called exothermic process. Exo means out. So system sends the heat out, and the sign for Q will be negative. Okay? This is very important. I want you to keep it in mind, memorize it. Instead of heat itself, let's talk about a property of the substance that we can use to measure the heat of reactions. So we introduce enthalpy and we show it in H. So what is H? What is enthalpy? It's an extensive property of the substance that can be used to measure heat, which is absorbed or released in a reaction. So H is a measure of that released or absorbed heat. What we said extensive property. What is extensive property? Extent means amount. So an extensive property depends on the amount of substance, like mass. It depends if you measure, let's say, 2 grams of substance or 200 kilograms, right? The balance will show you difference. And also volume is another extensive property. We also have other extensive properties, but mass and volume are the best of them. Okay, so enthalpy also is an extensive property, means depends on the amount of substance. If you have 1 mole of substance, you have different enthalpy than when you have 10 moles of substance. Of course, when you have 10 moles of substance, you have more heat and H is higher, larger. Also, we need to know about state function because enthalpy is an extensive property and a state function. So what is a state function? It's a property of system that depends on its present state. How do we explain it? It looks really weird. So here's a very simple example of 2 hikers, hiker 1 and hiker 2. They want to go from campsite A to campsite B. Okay? Let's show them in different colors so you can see better. Hiker 1 wants to take this route to go from campsite A to campsite B. But hiker 2 wants to take this route to get to campsite B from campsite A. What is important at the end is that both of them reach to campsite B, regardless of the pathway they took, right? This is the same in thermochemical reactions. state functions do not depend on how the system reached from initial to final. What is important that the system has reached the final situation, say final state. So this is called the state function, and enthalpy is a state function. If you measure enthalpy change, it's heat under constant pressure. So if you keep pressure constant during a reaction and measure the heat under constant pressure conditions, you can label it as delta H. And this is what we can measure for a reaction. So because H is a state function, delta H is final H minus initial H. That's in the concept of state function. For a chemical reaction, delta H of reaction, what is the final position? Isn't it for the products? Products are produced from reactants. So that's the final position of the reaction. And initial is the reactants. So delta H for a reaction is enthalpy of products minus enthalpy of reactants. We don't care what happened in between. We just need the product and reactants. Keep it in mind because you will need it later. Another formula based on law of conservation of energy, or Fair's law of thermodynamics, is the relation between enthalpy and internal energy. Don't forget, internal energy, we said, is the sum of potential and kinetic energy. So this is the formula that shows the relation between enthalpy and internal energy. H is U plus PV. What is PV? It's the energy, if you consider a cylinder and we have a weight on it, it's the energy that system uses to change the volume against the atmospheric pressure. Let's say the cylinder wants to expand and it uses some energy to expand against the pressure of that weight and atmospheric pressure. So it's called P delta V. So delta H will be delta U plus P delta V, and if you rearrange it, delta U, or change in the internal energy of the system, depends on delta H, or enthalpy change, minus the work of pressure volume. That's the formula that you can keep in mind. Delta U is equal to delta H minus P delta V. So we are getting closer to our goal to work on chemical reactions and combination of the chemical reactions. So far you just worked with chemical reactions, right? You wrote the chemical equation, or the chemical equation were given to you, and you were supposed to balance this equation. Now, if you have a balanced equation, chemical equation, followed by delta H value, and this delta H value is definitely in kilojoules per mole, in nothing else, you can call it a thermochemical equation. So a chemical equation followed by delta H value, which is expressed in kilojoules per mole. Let's work on an example to see what I mean, to understand it better. Look at this question. I preferred to choose the same questions in your textbook because I didn't want you to think that maybe I'm working on simpler questions. Fair enough? Okay. Sulfur, the formula for sulfur is S8. 8 atoms of sulfur get together to form 1 molecule of sulfur. Sulfur burns in oxygen to produce sulfur dioxide. The reaction involves 9.31 kilojoules per gram of sulfur dioxide. Write the thermochemical equation for this reaction. If you want to write the thermochemical equation for this reaction, we need to have delta H value in kilojoules per mole, not in gram. So we need to change it to mole. How? First of all, this is the equation for this reaction. S8 plus 8 oxygens gives 8 molecules of sulfur dioxide. Then we say it evolves, means it's an exothermic reaction, and exothermic, let's write everything. It's an exothermic reaction, and the sign for delta H is negative. So minus 9.31 kilojoules per gram, and we just need to use the molar mass of sulfur. S8 is 8 times 32 point something, so it's 256.5. Then you cancel out the grams, and you will find the amount of delta H in kilojoules per mole, which is minus 2.39 times 10 to the third kilojoules per mole. So thermochemical equation is that chemical equation followed by delta H, and don't forget, when we don't show anything, it's per mole, kilojoules per mole instead of kilojoules per gram. I hope it was clear. The next concept is whatever change you may need to make on a thermochemical equation, or let's say the chemical equation part, that change must be reflected in the value of delta H, because delta H is for that particular equation. What do we mean? When you multiply an equation by a factor, you need to multiply delta H value by the same factor. If you multiply the equation by 2, delta H must be doubled. If you multiply it by 3, delta H value must be tripled. And also, whenever you reverse an equation, you flip an equation, you need to change the sign for delta H. Because if the original equation was shows an exothermic reaction, so delta H is negative, right? When you flip that reaction, it changes to an endothermic. So the sign for delta H must show endothermic, must change to positive. Look at this example, it will explain it more. When sulfur burns, the same example, when sulfur burns in air, the following reaction occurs. You already have it, and we already calculated this delta H value. So we need to find delta H for decomposition of SO2. For decomposition of SO2 means to flip this equation. It shows decomposition of SO2. What should happen to delta H? Delta H must be reversed. But be careful. Here you have 8 moles of SO2. You need to have it per mole. This is per 8 moles of SO2. So you divide all the coefficients by 8, then you will have 1 mole of SO2, 1/8 of S8, sulfur, plus 1 mole of O2. And you obviously divide the value of delta H by 8 to give you 299 kilojoules. Okay, practice on these. In the next video, we work on the other half of this chapter.